Well, the covariance was specified. I copied it over here along with the joint PMF here so we could actually compute it. So I take the expected value of this, and this is just some function of x and y. So this is just totally valid g, x, y, right? I need e of x, e of y. I could get those. Let's get those ahead of time. So e of x is equal to, well, I could sum over all x and all y, x, p, x, y. So let's do it that way. Or I could have had the marginal first. I actually had the marginal right before. So let's do it that way. It was easier. So it's the sum over all x, x, p, x of x. Notice x is 0 with 0.4. That I don't even have to count. I'll just go 0 though, just to show you, times 0.4 plus 1 times 0.6. So one thing you could say here is marginally x is a Bernoulli 0.6 random variable. EY, I will use the same method. We already have the marginals computed, so we might as well use them. Y here, so I get 0 times probability y is 0, 0.3, plus 1, 0.3, plus 2, 0.4. So the expected value of y is 0.8 plus 0.3, so 1.1. Okay. All right, very good, very good, very good. So now, how do I do? Oh, these aren't squared either. Sorry. I'm losing it a little bit. I was thinking of the variance, so that's good. So now think about this though. This is sort of like a squared term. It's an xy term with two different variables. So that is a quadratic term with different variables. Okay, but it is not the definition of the covariance. All right, so let's now do compute this covariance. So covariance xy is equal to the expected value. So I'm going to just do it over, I'll do the sum over all values here. X and y, there should be 5 values in total. And every time I just want to take little x minus 0.6, little y minus 1.1, pxy. And I just have to write these 5 things down. All right, so if x and y are both 0, I get 0.66, right? So I get 0.66 times, so that's the function there, times probability. They're both 0, so that would be 0.1, plus, now let's put x0 and y1, that has 0 probability. Okay, I don't have to worry about that. X0 and y2. Well, then I get minus 0.6 and 0.9, so I get minus 0.54. Minus 0.54. And the probability is 0.3. All right, now let's go to this row here. So x is 1 and y is 0. I get 0.4 minus 1.1. So that's minus 0.44, and that probability is 0.2. For the next one, they're both 1, so I get 0.4 minus 0.1, so I get minus 0.04, and yeah, let's see, minus, yeah. So when they're both 1, minus 0.4, I get plus 0.4 minus 0.1. Yep, so times 0.3. And finally, when they're both, when x is 1 and y is 2, I get 0.4, 0.9, so that's 0.36. And the probability is 0.1. Okay, so that's what I get. So if I want to add these all up, I get Let's take the positive ones and add them together. I get 0.066 and 0.036, so that's 0.102. That's the positive ones. And then I have minus, and this might be too much for me. Let's see, 1.15, 0.162. Plus 0.088 and plus 0.012. And look, this is kind of cool. This is 0.1, so I get 0.262. So overall, I get negative 0.15. Okay, so the covariance can be positive or negative. In fact, if you look at the form for it, if you look at the form for it, E cov xy, you see you get this thing like this. Pxy. And if this is negative or positive, we're going to take this weight here and weight these contributions. So a negative covariance, in a sense, tells you that there is significant weight. There's more weight when they're on opposite sides of their respective means. So when x and y together have a heavy density, and x is above the mean and y is below the mean, I'll get a negative number here. So it tends to tell you, it tells you that they tend to vary in opposite directions together. All right, so when I have a likely xy combination, it tends to be true that the x is going above its mean and the y is going below. So they're kind of going in opposite directions. So that's the idea. So I suppose that's the case here. I don't know if we can tell by looking at it. It's pretty close to 0, so it's probably not very easy to tell. But as x goes up, can I see that y goes down? A little maybe, because here's the 0.1, and this is more heavy weight over here. So as x comes up from here, it seems to get bigger. X seems to get bigger, and y seems to get bigger this way. Maybe, it's hard to tell just from that. Okay, alternate form. There's an alternate form for computing this since E x minus EX y minus EY. E is a linear operator. I can say this is equal to E. Let's multiply it out in here. I get x y. This should be a capital Y. xy, and now I just have to multiply everything, minus EX times Y minus EY times X plus EX EY. But then the E comes through all of this, right? So this gives me EXY. It's impervious to scale multiples, so I have minus EX, that's the constant, EY, minus impervious EY, EX, and then the expected value, this is already a constant, so this is just EX, EY. These terms are all the same. I have two negative, one positive, so I have EXY minus EX, EY. All right, so we could have computed this, some probably more easily this way, by just computing the expected value of xy and then subtracting the product from that. So let's try to do that. So here we have EXY is just equal to the double sum little xy, pxy. So many of these are 0, right? There's only 2 that survive. So this is equal to, let's see, this one and this one survive. So when they're both 1, I get 1 times P11, so that's 0.3, plus when y is 2 and x is 1, I get 2 times 0.1. So I get 0.3 plus 0.2, 0.5. So covariance xy could be computed like this, 0.5, now minus exey, but we did that. That was 0.6 and 1.1. This is equal to 0.5 minus, let's see, 0.6 and 0.66, right? 0.66? Yep, 0.66. And we get minus 0.16. So I'm off by 1/100th. I think I must have, I just made some little error here somewhere, but I believe the theory rather than my arithmetic in this case. So, all right, so you can see how much easier that was. And actually, I trust this more. So do use this formula for computation. Although this explanation here will elude you if you go right to the short form. So you want to know this is the definition and why it's the definition, but then you know that here is a very nice way to compute it. Okay? All right, very good. Let's stop and I will see you on the other side.